The universe? Just saying the word conjures images of endless stars, distant galaxies, and profound mysteries. Among these, two questions stand out: how big is it, and is it even finite? These are not just academic curiosities. They are enduring cosmological puzzles that challenge our understanding of reality itself. For centuries, thinkers have grappled with the sheer scale of existence. What we can currently observe, the so-called observable universe, represents only a tiny fraction of what might truly exist. It is merely our cosmic horizon, limited by the speed of light, and the age of the universe. To truly grasp the universe's extent, we must delve into some of the most complex and fascinating concepts in modern science. These ideas push the boundaries of human comprehension. We will explore foundational theories like the Big Bang, which describes our universe's origin. We will also examine cosmic inflation, a period of explosive growth that shaped everything. Finally, we will consider spacetime geometry, a concept from Einstein's general relativity that might hold the key to whether the universe is truly finite or stretches on forever. Prepare to have your mind expanded. Our journey begins with the prevailing cosmological model, the Big Bang theory. This theory is the cornerstone of modern astrophysics, explaining the universe's evolution. It describes the universe's origin from an incredibly hot, dense state, a singularity of immense energy. From this point, all matter and energy we know today emerged. This momentous event, the Big Bang, occurred approximately 13.8 billion years ago. This age is a crucial number, defining our cosmic timeline. The Big Bang was not an explosion in space, but rather an expansion of space itself. This continuous expansion has been ongoing ever since, stretching the fabric of the cosmos. The observable universe is precisely what its name suggests, the portion of the cosmos from which light has had enough time to reach us. It is our cosmic neighborhood, defined by light's journey. This light has been traveling across vast distances since the very early moments after the Big Bang. It carries information from the most ancient structures. Due to the continuous expansion of space, the objects whose light we see today are now much farther away than when their light was emitted. This makes calculating distances tricky. The observable sphere, our cosmic bubble, has an estimated radius of about 46.5 billion light-years in every direction. This is a staggering distance, far greater than the universe's age might suggest. This immense radius indicates the total distance light has traveled from the most distant objects we can detect. It accounts for the expansion of space during its journey. It is important to remember that this 46.5 billion light-year radius is not the edge of the universe. It is simply the limit of our current perception, our cosmic horizon. Here is where the mystery deepens. The observable universe, as vast as it is not considered the entire universe. In fact, it is almost certainly just a small part of a much grander whole. The universe could be significantly larger than what we can currently see or detect. Our cosmic horizon is merely a boundary of information, not a physical edge. It is even possible that the universe is infinite in size, stretching out without end in every direction. This concept challenges our intuitive understanding of boundaries. A key concept for understanding this potential for a much larger, or even infinite, universe is cosmic inflation. This theory revolutionized our understanding of the early cosmos. Inflation was a period of extremely rapid, exponential expansion that occurred immediately after the Big Bang. It lasted for only a tiny fraction of a second. During this fleeting moment, the universe expanded at a rate far exceeding the speed of light. This rapid growth smoothed out irregularities and stretched space to immense scales. Cosmic inflation suggests that the universe expanded far beyond our current observational view. The observable universe is just a small patch of this much larger, inflated cosmos. This explosive expansion could have stretched the universe to an enormous size, making it incomprehensibly vast. It would dwarf our observable portion. If inflation occurred, then determining the true boundaries of the universe becomes incredibly difficult, if not impossible, with our current observational tools. We are limited by our horizon. The universe beyond our observable bubble remains a realm of theoretical speculation, yet it is a logical consequence of the inflation model. It is a universe waiting to be discovered, if ever possible. The profound question of whether the universe is finite or infinite is closely tied to its overall geometry. This is where Einstein's theory of general relativity comes into play. General relativity describes how mass and energy warp the fabric of spacetime. This warping dictates how objects move and how light travels through the cosmos. The overall geometry of the universe can take one of three fundamental forms, each with profound implications for its size and fate. These shapes are determined by the universe's total energy density. One possibility is a flat, or Euclidean, geometry. In a flat universe, parallel lines remain parallel forever, and the angles in a triangle always add up to 180 degrees. Another possibility is a spherical, or positively curved, geometry. Imagine the surface of a giant sphere. In such a universe, parallel lines would eventually converge. A spherical universe would be finite in volume but would have no boundaries, much like the surface of Earth. You could travel in one direction and eventually return to your starting point. The third option is a hyperbolic, or negatively curved, geometry. In this scenario, parallel lines would diverge, and the angles in a triangle would sum to less than 180 degrees. A hyperbolic universe would be infinite in extent, stretching out forever without end. It would have an open, saddle-like shape. It is important to note that a flat universe, while locally Euclidean, could also be infinite in extent. Its flatness does not automatically imply finitude. The geometry of the universe is a critical factor in determining its ultimate size and whether it has an edge or is truly boundless. It is a question of cosmic topology. So, what do our current observations tell us about the universe's geometry? The most compelling evidence comes from the cosmic microwave background, or CMB. The CMB is the faint afterglow radiation from the Big Bang, a snapshot of the universe when it was only about 380,000 years old. It provides crucial data about the early cosmos. Observations of the CMB, particularly from missions like WMAP and Planck, strongly suggest that the universe is very close to being flat. This is a remarkable finding. This observed flatness implies that the universe's total energy density is extremely close to the critical density required for a flat geometry. It is a delicate balance. However, this observed flatness, while significant, does not definitively prove that the universe is infinite. It only tells us about the geometry within our observable horizon. The CMB data reflects the geometry of the universe only within the portion we can see. It is like looking at a small patch of a vast surface. The true geometry could potentially differ beyond our current observational horizon. We might be living in a flat patch of a much larger, curved universe. For instance, a very large, positively curved universe could appear flat from our limited perspective, much like a small patch of Earth's surface appears flat to us. Understanding the true geometry and extent of the universe will require further advancements in cosmology and observational techniques. The quest for answers continues. The universe remains a profound mystery, a canvas of endless possibilities. While we have made incredible strides, the ultimate questions of its size and finitude still beckon us forward.